Today we are going to be going over some logic functions in R, and sampling and manipulating a vector. So the first thing we want to do is we want to set our working directory. So we go to Session, Set Working Directory, choose Directory. You want to just choose whatever folder you want for your knitted thing to save into. Open, and boom, done. Okay. Next, complete these steps. Leave the title be, change author to your name, change to today's date, and make sure the date is wrapped in apostrophes. Leave line 5 as is. Or let's leave 5 through 7 as is. Yeah? Okay. So let's get started. So if we want to sample a vector, which means we are taking one element of the vector and pulling it out one at a time. Sometimes we put the element back, and so each time we grab it, it'd be the same probability, but sometimes if we don't put the element back, then each time you take one, it changes your probability of what you're going to grab because your total sample space is shrinking if you're not replacing it. So first, in order to sample a vector, you need to create a vector. So let's create vector A. Okay? Now let's sample the vector without replacement, and each element has equal probabilities. Size 2. Okay? So all you do is you use the sample function, indicate what data set you're referring to, what vector. The size is how many you want to sample out of. And replace means every time you pull one sample, are you replacing it? If it's false, it means you are not replacing it. So if size was not less than 4, but greater than 4, then it would not work because you're not replacing as you pull out of the bucket. So say there were 5 you wanted to get, but there's only 4 in your bucket. And so on that 5th grab, because you're not replacing it every time, there's nothing to grab, so it wouldn't work. Now let's try sampling the vector with replacement, and each element has equal probabilities. So this time we're going to grab 12 of them. So we can grab 12 greater than 4 because this time we're replacing it. So every time we grab one, we're putting it back into the bucket. So each time it's a 1/4 chance that you're going to grab each one. But let's say that 1, 2, 3, 4 represents like different colored balls, like blue, green, yellow, red, right? And there's a different amount of each kind of those balls in there. And so we would put the probability of getting each one of those colored balls if they are different. Now, if there are the same number of all the different kinds of balls, then you can just use these functions. But if there's different numbers of each color ball, then you need to specify the probability that you will grab one vector or the other, or one color or the other. And the percentage, the probability needs to correspond to each element. So it's saying that, say 1 means red, so for red, there's a 5% probability. For, say 2 is blue is a 5%, where 3 is green, so green is 10%, and yellow is 70%. So what does that mean when we're looking at this bucket? what is there going to be majority of balls? What color are the balls going to be in majority? Well, they're going to be yellow. If yellow is the 0.7 one, then they're all going to be yellow. So let's go ahead and run this chunk, see what it outputs. So see, this one only grabbed randomly 2 elements. This one grabbed 12 elements, and this one also grabbed 12 elements. But now you can see that while these 12 elements, you know, there seems to be an equal-ish amount of each number, this one you can tell that 4 is by far the most predominant number, and that's because 4 has a 70% probability associated to it. Make sense? And if you were to run this again, we'd get different numbers. Yep, like here, this time you got all 4s. And so each time you run this, you're going to get different numbers because it's randomly sampling. Make sense? So logical operators. So you can't name variables true or false, and that's because true and false are a logical operator in R. So let's say we have 2 vectors. We have A, which is true, true, false, false. So you can either write true, false as a logical operator by writing true or false all the way in caps, or you can write it by just saying TF in caps. And vector B is true, false, true, false. So there are different kinds of logical arguments that we can query. So an exclamation point in front of a data set or an object does not mean negation. It means that not true is false and not false is true. So if you were to say A, right, it's going to look at this first element, which is true. So it says it means that true is that not true is false and not false is true. So this is not false. True does not equal false. So that means this is going to equal true. Right? Makes sense? You can do this scalar. So scalar is just looking at the first element. So if the first elements both are true, then it results in true, otherwise it's false. So here, A and B, this would output true because both the first elements are true. Versus you can do the same thing in a vector. So it's going to look at both elements. If both elements are true in each element of the vector, then it outputs as true. Otherwise, it's false. So what would come up here? So true, this one would be false because it's true, false. This one would be false because it's true, false. And this one would be false because it's false, false. So it should be true, false, false, false. Now, the AND function and the double AND function is for both elements to be true. Now, if you just are asking if one is true, then you can use the, I don't know what this is called, but like the vertical lines. If you want to do it scalar, so just the first element, if at least one of them is true, then it will output as true, so this one would be true. And for the vector, if at each element of the vector at least one is true, then yes, so this would be true, 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 false, right? Okay, let's try it. So this one, like I said, is not negation. It's like the opposite. So for A, the first two elements are true, true, so that means it outputs false, false. And the last two are false, false, so it outputs true, true. The scalar, you're looking at for both elements to be true in the first element, that's true, so that outputs as true. Now for each element, so both are true, true, false, 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 because none of the other ones are true, are both true. Scalar for at least one element being true, true, and then true, 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 false for vector, at least one is true. Make sense? Okay. So we can also make comparisons of vectors. So let's say we have these two vectors, x and y. So we want to know if x is equal to y at each element. False, false, true, false, false, right? Now inequality. So are x and y not equal to each other in each element? True, true, false, true, true. Now is x less than or equal to y? True, 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 false, false. Now is x less than y? So this one, it'll be true, true, false, 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 because 3 is not less than 3, it's equal. Now greater than or equal, so false, false, true, true, true. Now this will be the same thing here, false, 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 because x is not greater than y, they're equal, and then true, true. Make sense? So we can also ask if any of the elements are true in a vector, or if all of the elements are true in a vector. So let's say we have the vectors x, y, and z. So are any in x true? Yes, so this is going to be true. Are any in y true? Yes, so this is going to be true. What about all? Are all true in x? No, so this is going to be false. And are all true in y? Yes, so this is going to be true. So it should be true, true, false, true. True, true, false, true. Boom. Okay. We're getting into the good stuff now. So you can also filter with logic. So let's run this. And let's examine what each one of these mean. So we have two vectors here. We have x and we have bool. X is a numerical vector versus bool is a logical vector. So if we are saying, so when we do this x brackets something on the inside, we're basically saying in data frame x, look at bool. So well, in data frame x, it wants us to spit out the true values of bool. So the true values of bool are 2 and 4. Does that make sense? So it wants you to spit out the true values of x using this inequality. So x is greater than 3. That's only 4. So 4. X is greater or equal to 3. So 3 or 4. Make sense? So we can also we can do conditional filtering. So this is what we call if else. So if the corresponding values are equal, produce 0, otherwise produce 1. That's what this means. If the corresponding values are equal, produce 0. Otherwise, produce 1. So, x and y, are they equal? No. No for this first element. So would this produce a 0 or a 1? It would be a 1. They are equal, so it would produce a 0. Not equal, not equal. So 1, 1. So it should be 1, 0, 1, 1. 1, 0, 1, 1. Perfect. So we can do this more complex as well. So I'm gonna run this so I can explain the outputs. Okay, so we have a vector 1, 2, 3, 4. Our vector y is sampling vector x. You're pulling 3 of them and we're replacing them every time. So if we run this over and over, you'll see these 3 numbers change every time. Right? Okay, so now let's figure out how they got 2 from this. So it says if y1, so this is y1 is equal to 1, then output y2. Okay, boom. We didn't even have to do the rest of the conditions because y1 was equal to 1. So it output y2. So let's run this again to see if we can get something different. Okay, so if y1 is equal to 1, output 2. So y1 is not equal to 1, so we can't output 2. We can't output y2, which y2 in this case is 1. So we see here that our answer is 2, not 1. So we continue. Else if y1 is equal to 2, then output y3. And if y1 is not equal to 2, else put y1. So y1 is equal to 2 here. So we output y3, which y3 is 2, and that's why this is 2. So let's do this again. Okay. So if y1 is equal to 1, output number 2 of y. So is y1 equal to 1? No. So we move on. Is y1 equal to 2? No. So we move on. So because there's no other condition, we have to output y1, which is 3. Does that make sense? Okay. So now what we're going to do is I'm going to go over how to do these examples with you. You are then going to do these problems on your own. The problems are pretty much identical to the example. So just pay attention to what I write for the example and you'll be all set. So, example 1. Using the sample function, you'll use R to simulate selecting a number ball from a bucket. The contexts of the bucket are 1 ball marked 1, 2 balls marked 2, 3 balls marked 3, and 4 balls marked 4. So create 2 vectors, unique values on balls and proportions of each value. So, unique values on balls. So what would this vector look like? Well, the unique values on balls are 1, 2, 3, and 4. Oops. Now, what about proportions of each value? So what would these be? So there's 1 ball marked 1, 2 balls marked 2, 3 balls marked 3, and 4 balls marked 4. So how many balls total are there? 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. So there's 10 balls total. So that means that the proportions of each one is 1 out of 10 for 1. There's 2 balls marked 2, so 2 out of 10 for 2, 3 out of 10 for 3, and 4 out of 10 for 4. Now, what else could I do instead of this? Well, 1 out of 10 is 0.1, 0.2, 0.3, 0.4. So why don't we just do that so it's like in proportions, right? So 0.1, 0.2, 0.3, 4. Right? Okay. So we did that one. So use the sample function to simulate selecting a single ball from the bucket. Run this in the console just to see the output. So to do this, we're going to use the sample function. So sample. Now, what is our X? What is the data set that we're grabbing from? We're grabbing from the unique values on balls, right? So X equals unique values on balls. We are selecting a single ball, so our size is going to be 1. And we'll just say replace is true, because it doesn't really matter because you're only selecting 1 anyways. But because each one of these unique values on the balls has different proportions, we need to indicate the probability here. So it'd be prob equals proportions of each value. Okay, so let's run that. And we got an output, 3. So next, create one vector, expected number of each value. Its elements will represent the number of times you would expect to see a 1, 2, 3, or 4 if you repeated the selection 1,000 times. I believe there should be about 100 1s, 200 2s, 300 3s, and 400 4s. You should think about that. So that makes sense, because if you do 1,000 times 0.1, that's 100. 1,000 times 0.2, 200. 1,000 times 0.3, 300. 1,000 times 0.4, 400. So we're going to create a vector that's called expected number of each value. And so our thing is going to look like 100, 200, 300, 400, right? Okay, we are cruising along here. So create one vector, simulated observations. Use the sample function to repeat the process of selecting one ball 1,000 times. So if we only have 4 options, right, and we're selecting it 1,000 times, do we need to replace, or is replace going to be true, or is replace going to be false? So think about that while I type. So this is simulated observations. Use the sample function. X equals unique values on balls. Size equals 1,000, right? Because we're grabbing it 1,000 times. So are we going to replace it each time we grab? Yes, we are. Because remember, if the size is greater than how many elements are in the vector, replace has to be true, or otherwise the function will not work. And because the unique values on balls are different probabilities, again, we have to indicate what those probabilities are. And those probabilities are this vector, proportions of each value. So let's print this. And run it. So there's 1,000 times. 1, 2, 3, 4 were picked out. You can see just from this that 4 seems to be the most abundant number, and that's because 4 is the highest probability, right? So we're going to hashtag this out so it doesn't print that every time. So next, E. Create one vector. Observe number of each value. Use the table function to count the numbers of 1s, 2s, 3s, and 4s that appeared in simulated observations. So remember this. So all we do is we say observed number of each value. And we use the table function. And what do we want to use the table function on? We want to use it on simulated observations. And so we're going to print this so we can see how many. So I'm actually going to unhashtag that so we can see all of them come out. And so here's all of them, right? So how many times did each one appear? So 1 appeared 118 times. We assumed 100. That's pretty close. 2 came out 231 times. That's pretty close to 200. 3 came out 259 times. Now that's not as close, but it still rounds up to 300. And 4 came out 392 times, which is pretty close to 400. So our probabilities, when it runs randomly, also works out. So I'm going to hashtag that out again. Okay, F. Create one vector, absolute difference. Compute the absolute value of the difference between observed number of each value and expected number of each value. So now we're getting the percent error in which our expected matches our observed, right? So let's create this vector. So it's called absolute difference. We use the abs function, which means absolute value. We want to know the absolute value of the difference between observed number of each value minus expected number of each value. So to have that come out in the console, let's print it. Absolute difference. Run our code chunk. So simulated observations for 1, 2, 3, 4. Okay, so this is only, so 105, our expected was 100. So this is only a difference of 5. Our difference between 200 and 198 is 2. 312 and 300, 12. 385 and 400, 15. And it doesn't matter that this is 15 under and this is 5 over because we're taking the absolute value. So next we have G. Create one vector, absolute difference greater than 30. So use a comparison that checks each element in the absolute difference to see if it's larger than 30. So how are we going to do that? Well, we're going to create this vector. It's called absolute difference greater 30. And we're going to use the data frame or object that we made, which is called absolute difference, right? And we want it to be greater than 30. So let's print that. So are there any absolute differences that are greater than 30? Let's find out. So these are the absolute value differences. None of them are greater than 30, so they are all false. Now, this was checking each element in the vector, right? Now we want to make a logical vector that indicates true if any values in absolute difference greater 30 were greater than 30. So what we do here is we use the any function. So if any greater than 30, we use the any, and we want to know the absolute difference greater than 30. So if any of these are greater than 30, any of these are greater than 30, then the answer will be true. And if not, it will be false. So let's run this. So none of them were greater than 30, so it's false. Okay. Report whether or not any occasions report whether or not there were any occasions where observed number of each value had a difference of more than 30 from expected number of each value. Use inline code. So I didn't teach you what inline code is, but inline code is just typing in between these code chunks. So we can say, basically what we saw was that none of them are greater than 30, so the difference between observed number of each value and expected number of each value was never greater than 30 in all the times it was ran. So run this code several times. Your report should update with new values each time. So basically, like, before you come to this conclusion, run it like, I don't know, 10 times or something like that, right? And then see, and then count how many times it was true, how many times it was false. You have to do the same thing here, so you can do that. Okay, that is all for this lesson on logical operators. If you have any questions, feel free to reach out to me by email, and I hope you guys have a great day.